Okay, so let's move on. We're in the next section known as the law of sines. Now here's the deal. So far we've been dealing with right triangles, and with the right triangles we deal with our 6 trig functions. But you know as well as I do, we don't always deal with right triangles. So when I don't have a right triangle, there's 2 other laws that involve the trig functions that I could possibly use. One of those laws is the law of sines. Now, here's the time you can use the law of sines. The first case is when you know a triangle that has 2 angles and a side sandwiched in between them, or it has 2 angles and the side is outside of it. So let's take a look at this triangle. This is for case 1. If I know the measurement of 2 angles and the side in between them, then I can use a law of sines. Notice this isn't a right triangle. The other or for case 1 is if I have, this is still case 1, if I know the length of 2 angles and I know the length of a side not sandwiched in between them, so let's just say this side, I'm still able to use the law of sines. Okay? Now here's the deal. In both of these cases, if I know the measurement of 2 angles, I automatically can find the measurement of the third angle, right? It'll be very concrete, won't it? Okay. The second case is if I know 2 sides and the measurement of an angle, but notice the angle's not in between, right? So here is case 2. If I know the measurement of 2 sides and I know the measurement of the angle not in between those 2 sides, say this angle, then I'm allowed to use the law of sines. However, because I only know the measurement of one angle and it's not in between these 2 sides, this would be known as the ambiguous case, because depending upon the length of these 2 sides and how wide this angle opens or how not so wide it opens, this side, which I did not complete, may not touch ground. It may not touch this side. It's known as the ambiguous case. I could get a triangle out of here, and then again I may not get a triangle out of here. Okay, so we are going to deal with the ambiguous case in just a little bit, so hang in there. What I'd like to talk about is actually the law of sines. These 2 cases for non-right triangles, the law of sines is nothing more than a proportion. And let's make certain that we understand how triangles are labeled. So, if this is angle A, and this is angle B, and this is angle C, then the corresponding sides, the side opposite angle A would be called side A. Notice I'm using a little a versus a capital A. The side opposite angle B would be little b. Their corresponding sides. Okay? And the side opposite capital C is little c. Alright? These are called corresponding sides. The side opposite its angle. The side opposite its angle. The side opposite its angle. And the reason why I'm making certain you understand that is the law of sines is nothing more than a proportion. And it deals with corresponding angles and sides. So I could take the sine of angle A and divide it by its corresponding side, which would be side A. And that could equal the sine of angle B over its corresponding side, which would be side B. Okay? So I can set it up like this, or I could have it one of these equal to the sine of C over its corresponding side. Any of these 3 can be equal to each other. Okay? So it just depends what information you have. All right? So there's the law of sines. Here are the 2 cases that I can use them. And this ambiguous case, we're going to talk about next so we can understand it just a little bit better. Hang in there. Got a couple examples for you. Okay, so we're back. So let's talk about the ambiguous case. Before I get too far into it, I drew this right triangle here because I want to remind ourselves that if we have a right triangle and we're looking for the height of it, how would we find it? Notice here's angle A, and I have H, which stands for height, and B. Now, if you notice, H is opposite angle A, and B is the hypotenuse, isn't it? So which trig function involves the opposite side to the angle and the hypotenuse? Good, sine. So if I take the sine of angle A, that would be equal to H over B, wouldn't it? And to solve for H, which is the height, I would take the hypotenuse and multiply it by the sine of A, wouldn't I? Okay? This is how I would find the height if I had a right triangle, wouldn't I? Okay, so make certain you make note of that for yourselves. This is how I would find the height if I had a right triangle. Cool? Okay, now let's look over here at this case. This is a case where I would not get a triangle whatsoever, depending upon the information that's given. And here's the information that's given. Notice I have this side A, and it's a dotted line at this point because I know the measurement of two sides, but not the angle. Oh, pardon me, and an angle that's not included. So here's the deal. Here's the information given. If this side A is less than side B, okay? So if you allow me, this would be side A. It is definitely less than side B, isn't it? The other piece of information is if side A is also less than the height. Well, the height would be this side here, wouldn't it? So if side A is not only less than this B, but it's also less than the height, do you notice no matter which way I swing side A, it's not going to touch the bottom here, is it? So since it's not going to touch the bottom, I don't get a triangle whatsoever. My side here does not drop down to the base. So this is the case where you would not get a triangle at all, period. You with me? Okay. Remember, this is how you find the height. Now, let me look at another case where you would get one right triangle. So, let me draw. Okay. So here's the information that would need to be given in order for you to get one right triangle. You would need this side to be less than B. Okay? I call B the pseudo-hypotenuse because if you notice in this triangle, B is the hypotenuse. All right. So if side A was less than side B, right? Okay, got it. But side A literally was the length of the height. So, right here, if side A actually was equal to the height itself, it's less than side B, but it's actually equal to the height. If this is the case, then when I swing it in, it won't touch. When I swing it out, it won't touch. But if I draw it and it's the exact same length as the height, then I'm going to end up with one right triangle. Cool? Okay. So let's look at these two cases again, because there are two more we're going to work with, but let's look at these two again. On both of these, this side A is less than side B, the pseudo height, okay? In this case over here, A happens to be less than the height. That's why I don't have a triangle whatsoever. In this case, A is actually equal to the height, which is why I get one right triangle. Cool? Okay, I've got 2 more cases, so hang in there, I'll be right back. Okay, so let's talk about the last 2 cases for the ambiguous case. Let's look at this one over here. In this case, based upon the information they're giving us, we're actually going to get 2 triangles out of here. So let's find out how that happens. Sorry, there's angle A still here, okay? Now, one piece of information is that A is still less than B, okay? So, if this is side A, it is clearly less than side B. Agreed? But the other piece of information is now that A is greater than the height. So the height would be straight up and down like this, and if you allow me just a little adjustment, you guys are so good, so patient. I appreciate that. So A is still less than B, but it's greater than the height, right? Okay, so here's the deal. Here's what's happening then. If I take this side A and I swing it in, it's going to touch bottom, isn't it? It's going to create a triangle that looks like this, won't it? But if I take side A and also swing it out, it's going to create another triangle out here. So here's the deal. There's 2 triangles created. Since this side A is less than the pseudo-hypotenuse, but longer than the height, it's going to create this thinner triangle, so to speak, and then it creates this bigger triangle when it swings out. So the second triangle, and I'm going to erase this information right now because when it swung in, this is now side A. This is the triangle that has now been created. Okay? And the other triangle that's created still B, still angle A, and now the other triangle is that side A has swung all the way out here, okay? Here are your 2 triangles. Based on the fact that this side was less than the pseudo-hypotenuse, but it was longer than the height. Now, here's a great piece of information. These 2 angles that have been created based upon the 2 triangles. This angle is an obtuse angle, isn't it? Remember, obtuse means it's greater than 90 degrees. This is an acute angle, isn't it? That means it is less than 90 degrees, correct? This would be considered angle B because it is opposite side B. This is also angle B because it's opposite side B. Agreed? These 2 angle B's are supplementary angles. And do you remember what supplementary angles are? Supplementary angles, angle 1 plus angle 2, they must equal 180 degrees. So this is actually a very cool piece of information for us to know. That the 2 angles that have been created are supplementary angles. Good? Okay, so this is how I'm getting 2 triangles. A is bigger than the height, less than the pseudo-hypotenuse. So it swings in, touches bottom, swings out, touches bottom again. Good? All right, now let's look at this last ambiguous case. This last ambiguous case actually has side A being greater than the pseudo-hypotenuse. So here's side A, and it's longer than this B, side B, the pseudo-hypotenuse. And the other piece of information is that this side A, by the way, greater than or equal to, is also greater than the height. So not only does side A have to be greater than or equal to side B, and in this case it's a little longer, but it also has to be greater than the height. And when it does that, this angle can't swing in to create a triangle because it's too long, but it can swing out to create a triangle. So the triangle that gets created is one that looks like this, with angle B being over there. This is how I get one triangle. Cool? This is the information that needs to happen. Are you with me? Okay, so hang in there. I've got a couple of examples about this ambiguous case. I'll be right back. Okay, so let's look at this example. They're asking us to state the number of triangles and find their information if possible. So what I'm noticing here is they've given me two sides and one angle that's not included in the two sides, which tells me I'm dealing with the ambiguous case, because the ambiguous case says, you know, two sides and an angle outside. So let's look at the information that they have given us, okay? And if you want to label the triangle like you're used to with the information I gave you just a little bit ago, that's fine, all right? But I am going to call this A because that's what we called it before, and this side was B, and that means this side was capital A, opposite side A, right? Okay, so what I'm noticing is this. I'm noticing that side A is less than side B. This is what we know. Side A is less than side B. Because of that information, if I look back at the four ambiguous cases, that means I either have no triangles, here are my possibilities, no triangles, one right triangle, or two triangles. And there's one piece of information I need to find in order to help me figure out which of these three it's going to be. Correct, I need to know the height, because that was the other piece of information that actually will tell me which of these, right? So, we need the height. And remember how to find the height. The height is equal to our pseudo-hypotenuse B times the sine of A. So in this case, to find the height, you're going to take 4 and you're going to multiply it by the sine of 60 degrees. Now, I suggest you get a decimal on this because radicals aren't going to help us compare these numbers. And you do your work, I'll do mine, but I ended up with that the height is approximately 2.42, approximately. Did you get the same thing I did? Okay, so now I know that A is less than B. What I also know now is that A I'm sorry, I goofed. I thought I goofed. Forgive me. Because you're probably going, hey, I didn't get that number. Oh, that's good. You weren't supposed to get that number. You're supposed to get this number. That's what I get for not looking at my notes. You get that the height is approximately 3.4. One digit off will make a huge difference. Okay, so once again, forgive me. The height is 3.4. A is less than the pseudo-hypotenuse, but we also know now that A is less than the height. So which of these three cases has A less than B and A less than the height? Yep, right here. No triangle. I'm not going to get a triangle whatsoever. Why? Because if this side is less than B and it's less than the height, no matter which way I swing it, it will never touch bottom. Cool? Okay, so that's a case with no triangle. I got another one for you. So let me put it up over here. Let me draw it. Okay, so this is what it looks like when I draw it. Now, again, if you would like to label your sides to make sure that you have this variables to compare to, that's fine. This was our A, this was our B, this was our angle A. Now, we got to figure out what we know. What do we know? Well, in this case, we know that A is bigger than B, don't we? Okay, so go back and take a look. What's the possibility when A is greater than B? Yeah, there was only one possibility. The one possibility was what I had one triangle. So here's the deal though, to confirm it, you still need to know the height because there was two requirements. Not only did A have to be larger than B, but we need to know the height in order to confirm that we do indeed have one triangle. Remember how to find the height. The height is equal to B multiplied by the sine of that angle next to it. So, in this case, this was my answer. Height is approximately 2.42. So, A is greater than B, and A is also greater than the height, which means if it's greater than B and it's greater than the height, that means it's going to swing out and it's going to create this triangle. So I do indeed get one triangle. Are y'all with me? Okay. But the directions said, if possible, to find the information of this triangle. So let's take a look. I have two sides and an angle. Agreed? Because of this, I'm going to use the law of sines. And now, you're like, well, what do I find first? Well, remember the law of sines. You need to know two angles and two sides, right? Well, I have two sides. I have one angle. And since it's a proportion, the law of sines, couldn't I find the angle opposite side B? Couldn't I find angle B? So, if this is the case, then I would be finding the sine of angle B divided by the side opposite of it, which is 4, and this would equal the sine of 30 degrees over its opposite side, which is 5. Cool? Okay, so we need to do some algebra here, and I would have to do the sine of B equaling 4 times the sine of 30 degrees over 5, and then I would have to take the sine inverse to get rid of it from the B, wouldn't I? Of this wonderful looking fraction. Okay, so you do your work, I'll do my work. I've already done this, and hopefully the two of us will agree, or the however many of us will agree on what angle B is equal to. Let's see. Yep. Notice I put a few extra digits there. Okay, so I ended up with B is approximately 23.6 degrees. Did you get that? I hope so. So angle B here has a measurement, a value of 23.6 degrees. Good? Does that make sense? Okay, so now take a look. I know angle A and I know angle B. Couldn't I find this missing angle up here? That would be angle Yes, this one would be angle C. Okay, so let me gather myself some board space so we can continue this and it doesn't look so messy. All right, by the way, notice I did a little goof, but I'm sure you guys caught it and fixed it. This is why you need to do the work with me. Why? Because I'm human. Sometimes I calculate, punch in the wrong numbers with my fingers, and that's what happens to us. But gratefully, it's still one triangle. Okay, so I'm going to try to clean up this triangle over here and redraw it so it looks a little bit nicer for us to work with. So I'm just redrawing this triangle, labeling it a little bit better, a little bit cleaner. Here's the side of 4, here's the side of 5. This was 30 degrees. We just found this was 23.6 degrees, right? And now I'm working on finding angle C. Well, gratefully there's how many degrees in a triangle? Good, 180. So if I take 180 degrees and I subtract the other two angles, what do you get? I ended up with angle C has a measurement of approximately 126.4 degrees. Did you get the same? Okay, so I found angle C, good, but I still need to find side C. I need to know the measurement of side C. So here's the deal. To find side C, I'm going to stick with, obviously, the law of sines. So side C would be over the sine of the angle opposite, wouldn't it? And then I can choose any other proportion or ratio that I want. I'm just going to go with an original one that I already had. I had 5 over the sine of 30 degrees. Good? Okay. So when I solve for C, I would need to multiply both sides by the sine of 126.4 degrees, wouldn't I? Okay, so C would be approximately equal to, I have 8.05. Does that make sense? Okay, let me go back and recap a second. The original information we had was side B was 4, side A was 5, angle A is 30 degrees. We knew that A was larger than B. And that gave us a possibility of one triangle. We needed to verify it was going to be one triangle by finding the height. And to find the height, we had to do B times the sine of A, angle A, which gave us a value of 2, which means A was also larger than the height. So since it was larger than B and larger than the height, it was going to swing out and create this triangle. So I did indeed have one triangle. Using the law of sines, I was able to find angle B here. So I had to take the sine of angle B and divide it by the side opposite it, which was 4. And I equaled that to the other ratio of sine of 30 degrees over its opposite side of 5. So notice I put both the signs on top, both the sides on the bottom. And when I did my algebra, I ended up with angle B being approximately 23.6 degrees. Good? Okay, so back over here we redrew the triangle. So here's our 30 degrees and our 23.6 degrees. And that was easy to find angle C. Just subtract from 180. And the last thing we had to do was find the side C. So notice I put side C on the top, which means in the other ratio I had to put a side on the top. So I put 5 on the top. Side C was over the sine of its opposite angle, 126.4 degrees. 5 was over the sine of its opposite angle of 30 degrees. To get little c by itself, multiply both sides, and after you do all your calculator punching, it's approximately 8.05. Cool? Good. I've got one more example, so hang in there. I'll be right back. Okay, so one more example about the ambiguous case. Here's the information we have. What do we know? And again, I'm going to label these. So we know that side A is less than B, right? So, possibilities. No triangle, one right triangle, or two triangles. And in order for us to determine which of these possibilities we're going to get, we need to know the height. And to find the height, we're going to take B, which is 5, and multiply it by the sine of angle A, which is 29 degrees. Now, that number I've been wanting for the last two problems is here. The height is 2.42. So here's what we know. Not only is A less than B, but we know that A is greater than the height. So, based upon these two, I'm going to end up with two triangles. You're like, how is that going to happen? Okay, so just watch. So since I have two triangles, I need to find one of them. And when I find one of them, I can find the other one. So, just like that last problem, I have the two sides, and I have angle A opposite side A. Couldn't I find angle B opposite side B? All right, so here we go. So to find angle B, which is over here, and I haven't drawn it yet because I don't know the measurement of angle B. So once I know the measurement, then I'll be able to draw it. So bear with me. I know I'm going to find the sine of angle B, which is unknown, and divide it by 5, which is the side opposite of B. And that's going to be equal to the sine of 29 degrees over 3, which is its opposite side. All right, doing your algebra, the sine of B is equal to 5 times this wonderful fraction, correct? And you would have to take the sine inverse to get rid of B, wouldn't you? Okay, so by the way, I never punch all of this into the calculator at one time. I would figure out this fraction inside the parentheses and then take the sine inverse of it. That's me, because if I make an error punching something in, yeah, it's going to show up. I'm going to just have all my work wasted, shall I say. Okay, so in this particular case, when I did this work, I am ending up with angle B being 53.9 degrees, which tells me that the side of this triangle swung out because now this is an acute angle of 53.9 degrees. You with me? Okay, so can I find angle C? I sure can, because angle C is going to be equal to 180 degrees minus the 29 degrees minus the 53.9 degrees, which means in this case angle C is approximately 97.1 degrees. Cool? Okay. So, one more piece of information is side C. So, to find side C, I am going to take side C and divide it by the sine of the angle opposite it, which was 97.1 degrees. And that's going to equal, and I can use any proportion I want. I always go back to the original proportion. I have 3 over the sine of 29 degrees. I have to multiply both sides by the sine of 97 degrees, don't I? Okay, so when you do that, hopefully you get the same answer I do. I get C is approximately 6.14. Cool? Okay, remember, I took this and I multiplied it to the other side so I could cancel it off. All right, you with me so far? Okay. Now here's the deal though. There's supposed to be 2 triangles here. We found the one triangle. This is what the one triangle looks like. Angle C is right here. Side C is right here. But there's a second triangle, isn't there? And you're like, how do I find the second triangle? All right. It's not as bad as you think. Remember what I mentioned. This angle and the other angle for triangle number 2 are supposed to be what kind of angles? Yeah, they're supposed to be supplementary angles. Which means if I take 180 degrees and minus the original angle B that I found of 53.9 degrees, this angle B on triangle 2, this angle B would be equal to 126.1 degrees, which means this side of 3 is going to swing in. Which means this angle B in this case is going to be equal to 126.1 degrees. There's my second triangle. And you would find angle C and side C the exact same way we found it over here, except now using 126.1 degrees instead. So I would have a 3 here, a 5 here, 29 degrees, 126.1 degrees. I would find angle C by subtracting from 180, and then find side C by this similar process. Cool? Okay, so here is how you end up with 2 triangles. With me? Okay, you have fun with this, and stay tuned. I got some applications. Okay, so in this particular section, we are going to be dealing with applications for the law of sines. So here's our first problem. It says to consult the figure to find the length of the span of a proposed ski lift from A to B. A surveyor measures the angle DAB to be 25 degrees and then walks off a distance of L, which looks like it goes from A to C, of 1,200 feet, and then measures the angle ACB to be 15 degrees. They want to know what's the distance is from A to B. Okay, and then they ask it not to round until the final answer to 2 decimal places. Okay, so we got an idea of what's going on. Let's go to some scratch work, shall I say, and let's redraw this figure. So we have got would be there's angle C, there's angle B, here is A, and here is D. Correct? And they told us that this was 25 degrees. They said this angle happened to be 15 degrees, correct? And from A to C was 1,200 feet. Yes? Okay. And so now, they're asking us for this distance from A to B, aren't they? All right, so here's the deal. I have a triangle, and I have one angle, and I have one side of this triangle. The triangle we're looking at is triangle ACB. I only have one angle, and I have one side of it. Now, here's what I'm noticing. I'm noticing I can find a second angle very easily. Do you notice this angle has a measurement of 25 degrees? This line implies this is 180 degrees because it's also known as a straight angle. And a straight angle, which looks just like a line, measures 180 degrees. So if part of that angle is 25 degrees, then the other side will be 155 degrees. Do you agree with me? And if you're going, how'd you get that? Well, I took 180 degrees and subtracted the 25 degrees to get angle CAB. Good? Okay. And now I'm also noticing one other angle I can find. I can find angle B over here. Because I know that in any triangle, all three angles, as we have discussed before, add to 180 degrees. And if I've got a 15-degree angle already and a 155-degree angle already, then the measure of angle B would simply be 180 degrees minus the other two angles, which means angle B has a measurement of 10 degrees. Does that make sense? Are you with me? Good. Okay, so now let's look at what we're trying to find. We're trying to find from A to B. We're trying to find this distance from A to B, aren't we? Okay, so I'm noticing I have a side and a couple of angles. I have an angle, side, angle situation. That is the law of sines. Law of sines will deal with angle, side, angle. So that's the law of sines. I'm trying to find D. So to find D, I'm going to take that side and I'm going to put it over the angle opposite that side, which means it's going to be divided by the sine of 15 degrees. Do you agree? Good. And then I'm noticing that the only other measurement for a side is 1,200 feet. So since I put D feet on top on the other one, I'm going to put 1,200 on top over here. And the 1,200, the opposite angle is 10 degrees, so the sine of 10 degrees. Cool? All right. Just doing some algebra, I am going to have to multiply both sides by the sine of 15 degrees to get rid of it and to get the D by itself. And after you do some calculator punching, by the way, please make certain your calculator is in degree mode. If it's not in degree mode, you're going to come up with a rather funny looking answer. I have the distance to be approximately, and they asked me to round it to 2 decimal places, 1,788 and 5/800 feet. That would be the distance from A to B. Good? Cool. Loving it. Okay, let's check out another problem. We have a triangular plot of land. On one side, along a straight road, it measures 185 feet. A second side measures 22-degree angle with the road, and a third side makes a 21-degree angle with the road. How long are the other two sides? Okay, so let's check this out. First thing they told me is that I have a triangular piece of land, right? And we're going to call this the road. And they told me that it measures 185 feet, correct? And they told me that one angle with the road measures 21 degrees, and the other angle to the road measures 22 degrees. Cool? Okay, and their question to us is, what's the measure of these other two sides of this land? Okay, so what I'm noticing is I have another angle side angle situation, which, since it's angle side angle, means you are dealing with the law of sines. So, do you notice that you would be able to find a third angle here? Very easily, as a matter of fact. This angle up top can be found very quickly, yes? Okay, so you find that angle, because I found that angle, to be 137 degrees. Now, these other two sides, I'm just going to call one of them A, and I'm just going to call the other one B. Why? I just need something to talk about. I need a variable to talk about just to make life a little bit easier. Okay, so to find side A, we have the law of sines we're dealing with. So I'm trying to find A, which means I'm going to put that side over the angle opposite it. And, I know the 185 feet, so I'm going to put 185 feet over the angle opposite that. Cool? Okay, now some of you may be going, now wait a minute, wasn't the law of sines have the sine on top and the side measurement on the bottom? That's true, but the great thing about proportions is you can always flip them over and you still get the exact same answer regardless. And so since I don't like to have a variable on the bottom, I'm going to set it up with my variable on the top. Now, to get A by itself, you're going to have to multiply both sides by the sine of 22 degrees. Agreed? All right, so this is what the algebra looks like. And you get on your calculator, I'll get on my calculator, and I have side A being equal to 101.62 feet. All right, now to find side B. Do you think we're going to do it any differently than we did A? Nope, pretty much the same. I'm going to take the side B and I'm going to divide it by the sine of 21 degrees, because 21 degrees is the angle opposite side B. And that's going to equal the 185 feet over the sine of 137 degrees. Cool? Okay. Work on your algebra. Get that sine of 21 degrees out of that denominator. Again, please make certain your calculator is in degree mode before you even start doing any of this work. Okay, you do your work, I'll do mine, and I end up with 97.21 feet. Hopefully we're in agreement. Cool? Okay, let's take a look at another problem. Pat needs to determine the height of a tree before cutting it down to be sure that it will not fall on a nearby fence. Yeah, that wouldn't be good, right? Extra expense if it falls on the fence, because now you need to repair the fence. So good idea to know the height of this tree. The angle of elevation of the tree from one position on a flat path from the tree is 60 degrees. And from a second position that's 20 feet farther along the path. The angle is 40 degrees. And now they want to know the height of this tree. Okay, so I don't know about you, but I need a picture, because if I don't have a picture, I'm not sure what this is looking like. So I'm going to draw my tree. All right, and they told me along a path to point H, this was a 60-degree angle, correct? Right, on a flat path from the tree to H is 60-degree angle. So this is my angle of elevation to the tree, 60 degrees. And then they walked, this is to H, they walked 20 feet more to L, and now they figured out the elevation, angle of elevation to that tree was 40 degrees. And now they're still asking me for the height of this tree. Okay, so let's take a look. So I'm noticing I have two triangles. This particular triangle over here right next to the tree, that's a right angle, isn't it? So that's great, because since it's a right angle, that makes this a right triangle that's right next to that tree, which makes life a little bit easier to work with. I have Pythagorean's theorem I can use, and I have my regular trig functions I can use. But then I'm noticing the second triangle from H to L, and then up to the top of the tree. And I have two pieces of information over there. I have one angle being 40 degrees and another one being 20 degrees. Okay. Do you notice something about that second triangle? We did it in one of the other problems. Do you notice this angle right here? We can find it, can't we? Because this is a straight angle, isn't it? And if this is 60 degrees, then this would be good, 120 degrees, wouldn't it? Loving it. Okay. So in this triangle, H to L to the top of that tree, I've got an angle side angle situation, don't I? Okay, so once again, angle side angle means you're going to deal with the law of sines. Now, we have to know what we want to find. Okay, we got to know what we want to find. If, and let me label this to make certain that we're all in agreement. If I knew this side right here, isn't that the hypotenuse? And if I knew the hypotenuse, wouldn't I be able to find the height of the tree? Wouldn't I be able to find H here? Whoops, and let's not call it H because I have too many H's floating around now. So wouldn't I be able to find the height of this tree? Because, notice, I have a 60-degree angle. I'm trying to find the opposite side. If I knew the hypotenuse, then I could deal with which trig function. Good, I could deal with sine. I could find the sine of 60 degrees, and that would be t over h. I would be able to find t. But in order to find t, I need to know that hypotenuse, don't I? Okay, so in this other triangle, we're dealing with the law of sines. I'm trying to find h. So I could take h over the sine of 40 degrees, couldn't I? Good. And I have one other side of 20 feet, don't I? So I could have 20 on the top, because h is also the length of a side, and I need it over the sine of, I need to know the angle measurement opposite 20 degrees. I need to know this angle measurement, don't I? Okay, so I have 120, I have 40, so I have 180 minus 120 minus 40, right? Which means this is a 20-degree angle, isn't it? Love it. So, to find h, let's get our algebra. I need to move over the sine of 40 degrees. Divide still by the sine of 20 degrees, which means h is approximately, and by the way, do not get rid of this out of your calculator. Leave it in your calculator. I'm putting it on paper rounded to 2 decimal places because I need something to write. But do not round until the final answer. Remember the directions. Do not round till the final answer. So now that I have h, I can come back over here and I could say the sine of 60 degrees is equal to t over, and again, do not get rid of this in your calculator. And then when you get t by itself, it's going to be 37 point whatever's in your calculator times the sine of 60 degrees, isn't it? Okay. So I don't know about you, but when I did the work and rounded to 1 decimal place, I have 32.6 feet. What do you think? Good? Makes sense? You got that? Okay, cool. Let's look at another problem. Adam must fly home to City A from a business meeting in City B. One flight option flies directly from City A from B. That's about a distance of 453 8/10 of a mile. There's a second flight option that flies first to City C and then connects to A. The bearing from B to C is 29.4 degrees east, and the bearing from B to A is north, 59.8 degrees east. The bearing from A to B is south, 59.8 degrees west, and then the bearing from A to C is north, 78.2 degrees west. They want to know how many more frequent flyer miles will Adam receive if he takes the connecting flight rather than the direct flight. And you're like, I really don't care. And I understand that. However, this is a very good problem for a number of reasons. It's getting you used to your compass measurements. Okay, we have north, south, east, west. You're going to need to know those directions in order to at least draw a picture on this problem. Are you with me? Okay, so remember, he's flying home to City A, and he's starting in City B. So let's go over here on some blank paper, and let's start drawing ourselves a picture. So I have got City B, and he's flying to City A, and they told us that was 453.8 miles, didn't they? Okay. And he could take a connector instead to City C and then fly home to A. All right, so let's check this out and see what's going on. So there is from City A to B, 453 8/10 mile. Second option goes to C first and then to A. All right, so here it is. We have a bearing from B to C that is north 29.4 degrees to the east. All right. We have a bearing from B to C. You go north, and then you're going to the east, and east is to the right. 29.4 degrees. Okay? You with me? We went north, and then we went towards the east. And then we have a bearing from City B to City A of 59.8 degrees east. So now, north again, still to the east, but now I'm going to City A. And they said this was 59.8 degrees. Are you with me? Okay. So, got that bearing. And then it says the bearing from A to B is south, 59.8 degrees to the west. So, from A to B, First we go south, and then we're going to the west, 59.8 degrees. And it says from A to C is north, 78.2 degrees to the west. So now, from A to C, we're going north, and then we're going to the west, 78.2 degrees. Are you with me? Okay. So we have to be careful of the bearings. North to east, south to west, north to west. So it's a matter of knowing your compass, and starting from the city it's asking you to start from. So there's a lot going on right here. So I'm going to because you see the triangle, I know you do. So I'm going to take this triangle and I'm going to pull it out of all of that. So here's what I'm seeing. Here's B, here's A, here is C. I know this is 453.8 miles. That's about the only thing that I truly know about that triangle. But I say that I can find angle A. And here's why I say it. Here is angle A right here. Do you notice this is a straight angle? And a straight angle is how many degrees? Good, 180 degrees. Do you notice on either side of it, I've got two angle measurements? So, to find angle A, I would have to take that 180 degrees, subtract the 78.2 degrees, and subtract the 59.8 degrees, wouldn't I? And when you do that, I got that angle A is actually going to be 42 degrees. Cool. So, I have one more piece of information in the triangle that is clearly formed. Now, let's look at where angle B is. All right? Angle B, is angle B actually 59.8 degrees? That's the question. I'm hoping you said no, because this line, or this angle mark, tells me that whole thing from the north to here is 59.8 degrees. I don't want all of that. I just want this little piece right here. Okay, so do you notice that this little section is 29.4 degrees? So what do you think I would have to do to really find the measurement of angle B? Good. I'm hoping you said subtract. I'm hoping you said you have to take the 59.8 degrees and subtract the 29.4 degrees. And when you do, I get angle B really as a measurement of 30.4 degrees. Cool? Okay, so here it is. Here's the triangle I'm really working with. And once again, it looks like an angle side angle triangle, which means we got to deal with the law of sines. Okay, now I need to find the distance from B to C, and I need to find the distance from A to C. So looks like we have two more problems to work on here. All right, so let's find from B to C first. So I'm trying to find the distance from B to C, and I am going to divide that distance by the sine of the angle opposite it, which is 42 degrees. And, I know I have 453.8 miles, but I need to divide it by the sine of the angle opposite that, which is this angle C, isn't it? All right, looks like I have one more piece of the puzzle to find. You know what you got to do? I hope so, because I found this measurement to be 107.6 degrees. Remember, 180 degrees in a triangle. So 107.6 degrees. Okay. Let's do our algebra. Move the sign of 42 degrees to the other side. And again, before you do this, please make certain your calculator is in degree mode. If it's not in degree mode, you're going to get a funny answer. So I have the length from B to C as 318.56 miles. Did you get that same answer? I hope so. All right. Now, I need to find from A to C. Okay, so A to C is going to be divided by the sine of the angle opposite, which is 30.4 degrees. And again, it's going to equal the 453.8 over the sine of 107.6 degrees. Do your algebra, move over that sine of 30.4 degrees. And again, please make sure your calculator is in degree mode and don't round till the very end. So I have the length from A to C to be approximately 240.92 miles. Okay, so let me do some marking this down so we can see it. B to C we found was 318.56 miles. A to C we found was 240.92 miles. So here's the deal. If he decides to take the second flight and go from B to C and then home to A, how many miles will that be? Go ahead, do your figuring. I'll be back. Okay, so hopefully we agree. I ended up with, if he took the second option, which is B to C to A, that's a total of 559.48 miles. Okay, cool. But if he took the direct option flight, the direct option, which was B straight to A, that would be only 453.8 miles, wouldn't it? Okay, so if he wanted more frequent flyer miles, what would you have to do to figure out how many frequent flyer miles this guy's going to get? Yeah. Additional frequent flyer miles. You would simply subtract the second option and the direct option, and this guy would get 105.68 additional frequent flyer miles if he went with the second option. So, might be beneficial, might not. I think it depends how much additional time it's going to take too. But that's just my opinion. Cool? Are you with me? Okay, one more. We have Coast Guard Station Able, located 100 miles due south of Station Baker. A ship at sea sends an SOS that is received by each station. And the call to Station Able indicates that the ship is north 55 degrees to the east, and the call to Station Baker indicates the ship is south 60 degrees to the east. So they want to know how far each ship is from the, how far the station is from each ship. Okay, I don't know about you, but time to draw a picture. Love it. So we have Station Baker, and 100 miles due south of it, as they told us already, is Station Able. We got 100 miles. We have the ship over here that's in distress. They told us from Able we go north 55 degrees to the east. And from Baker, they said go south 60 degrees to the east. And they want to know how far is each one from the ship. How far is Able and how far is Baker from the ship? Okay, do you see it? I have an angle side angle again, don't I? Yep, law of sines again. Getting to recognize that? Hope so. Okay, so I'm hoping you noticed by now, because we've had this happen a few times, I'm probably going to need to know this particular angle right at the ship itself. You do your math, I'll do mine, but I found this to be a 65-degree angle. Okay, so I want to know how far Able is. I need to know the distance Able to the ship. So we have side A is what we're trying to find, and it's going to be divided by the sine of 60 degrees, because 60 degrees is the angle opposite. And I have that 100 miles, and yep, looks like I needed that 65 degrees, doesn't it? You're probably going, yeah, that wasn't a surprise. Okay, do your algebra. Both sides being multiplied by the sine of 60 degrees. Again, make sure your calculator's in degree mode. I ended up with Able is 95.56 miles away from the ship. Okay, let's find the distance from Baker to the ship. Okay, so Baker is going to be divided by the sine of 55 degrees, because that's the angle opposite of Baker's distance. And again, 100 miles divided by the sine of 65 degrees. So, do your algebra. Multiply both sides by the sine of 55 degrees. And again, I know I sound like a broken record, but make sure your calculator is in degree mode. I end up with 90.38 miles. So, which station is closest to the ship? Baker wins. Baker's closest to the ship. Baker should send out the search party, the rescue party. Cool? With me? Okay, you have fun with these applications. I'll catch you on the flip side.